I see somebody has edited my introduction. I was a little more snarky before. I blame Ash. Yeah, okay. Thank you for the warm introduction, Matthias. Matthias? Okay. Yeah, okay. And I'm looking forward to giving this talk. If anybody has any questions at all, I want them to be dropped in the chat right away. Matthias will bring it up between slide changes and we can have a conversation about it. I don't want to lose anybody along the way. This is a nice small group, so please do. If you've got a question, somebody else probably has that same question and it's too awkward to ask it. So please do be the encouragement of that conversation. We're all here to learn. So welcome to the talk about scaling and distributing a web application. My name is John Oram. Click. The goals of this talk are basically to introduce the complexities that come with a production level system. During university, I did a lot of coding on little projects that the classes had, but I never saw them applied to a scale of what I saw when I got into the industry. So I want to show that difference. It's going to be a very simple project in my eyes that we're going to be working on. And that project is the code is not the complex part. The infrastructure is going to be what gets more complicated over time. Yeah. Hopefully this is going to be targeting junior aspiring devs, junior level. Again, if I use any technical terms that nobody knows, please do bring it up. I try to talk at a sensible level, but sometimes I forget that not everybody has the same lexicon I do. Assumptions. Hopefully you have a little bit of coding background. If you don't worry too much. There's only a small part of coding. And I will be doing it and screen sharing it and talking through it. So hopefully you can follow along. And also hopefully you have a background in a little bit of what web communications look like. So just HTTP post, GET, all that. Again, if you don't know, we're going to reiterate a little bit of that. And hopefully what you'll get from this is a bit about how queues work, a little bit of Reentry Code knowledge, and ways to scale databases. A little bit about me. I used to like mountaineering and caving a lot. Here's a picture of me in the Bugaboos and in a cave, playing with distilleries. And now I have 2 kids, so I don't have a lot of time for that anymore. It's still an enjoyable life, just a very different one. So let's jump right into it. I have this example application that I've written for you. It's called What Is This a Pictureof.com. And what happens is you give it a picture and the system will then tell you what it's a picture of or what it thinks it is. So the interactions look like this. Somebody using the website gives a picture through an HTTP post request. Don't worry if you don't know what that means. The server looks at it, thinks about it, does some computation, looking at the image, writes some stuff to a database. A database is a different location to store data. And then it eventually comes back and says, this is a picture of an apple, or whatever it might be. So let's demo the website. What is this a pictureof.com? This is a very fancy website that I've built. It is got a picture a landing page where you can choose a picture. I have a couple of test pictures. Let's upload these tacos. It will take the picture, think about it, write some stuff to the database, and eventually respond. Now, what it actually has to do behind the scenes is it's got a file on disk that it has to load into RAM when it first hits this website, and I haven't been polling the website, so this might take a little while to load. If it gets past 30 seconds, it will time out. So, it thinks it's a plate. Okay, there you go. Took a long time, but it made an educated guess. There is a plate in the picture, so I call that correct. And other things that you might, that I did for fun, because I spent half a day building this, I had some spare time, I went and made a tag cloud. So, hey, look, a lot of Egyptian cats were uploaded. I tested with an Egyptian cat, tiger cat, tabby. There is a different cat. Yeah, there's a different cat in there. So every time somebody uploads a picture, I store it and I show it to people. So if you upload anything inappropriate, please don't. It will appear on this website. I'll have to go and delete it. And here is just every single picture that has been uploaded. Somebody uploaded a picture of a stage here, beer, glass. A lot of these are somewhat correct, and a lot of these are completely ridiculous and wrong. I think this was supposed to be Alps, and the cinnamon bun is not an espresso. So 10 lines of code to detect it. It's not going to be perfect. Okay, hopping back. I'm going to show you another tool, a tool that we can use to test this, to test a website. It's called Insomnia. It's actually written by somebody in Victoria originally. And it is a tool for sending those same requests that we just saw happen, but in through a different UI, not with HTML, front-end, JS, all that stuff. And if you've heard of the tool Postman, it's like that. I just grew up with Insomnia instead of Postman, so I'm showing you Insomnia. So here's the tool. I've hopefully enhanced the font size so you can see it. Please yell in the chat if you cannot. I will try and enhance the font size more then. I am making a post request to this URL here. What is this? A Pictureofcom /API v0 image. I'm pushing an Apple picture in this data, and I think that's it. And here's what I get in as a response. It is the ID of the image and what it thinks it is in a comma-separated list. When you make a request to a website, you can make many types of requests. That's called a method, the different types. So the method of get is when you just want to get some data from the website and you're not wanting the website to change in any way. When you want it to do some processing logic on the website, on the server side, that's what a post request is. So I'm doing a post request because I want it to do some processing. And the status code behind the scene, or with the response. So when it responds, a number is given to the response as well and says this is the status of it. So if you have heard of HTTP status 200, that's what this is. That's the everything's okay. I'm giving you a valid response. It worked as expected. There could also be, 301 or 500 levels or 400 levels, and they're all errors or redirects or what have you. They're just saying this is a different type of response than just a here's your content. So here, let's give this a try. I'm going to send it this apple. It's going to take probably about as long, almost 30 seconds. I probably should have clicked this before talking about status codes. And hopefully it comes back and it tells me those 3 tags. And we could go and upload a different picture. They did. Okay, so it thinks it's a pomegranate, Granny Smith, or banana. It's a picture of an apple. I don't know if it's a Granny Smith apple. And it took 20 seconds, which is ridiculously long. Here's some headers, the extra metadata around this, and it was 93 bytes. Okay, I've shown you this tool. Now, I want to simulate load. What I'm going to do is I'm going to right-click this and say, repeat on an interval. As fast as possible, please. So now every half a second, it's going to make a request. Now, eventually, if we sit here for longer than I want to in a talk, it will actually tip over the server, and the server is going to die, and then the website's down for about a minute. But I'm just uploading a bunch of apples to the website right now, and it will, oh, it's a bigger server now. So it won't die, but it's just going to upload a lot of apples. But you can imagine that a 503 would have come back here. I apologize that my demo did not work. And this 503 that responds is going to, a status code 503 up here would be the the server has died with an internal server error and we've run out of memory. It's because we ran out of memory if that actually did happen, but it didn't. Okay. Too bad we did not kill the server in the demo. Okay, so I'm going to talk a lot about scale in this talk. Scaling that web application. Right now it's a single server, as you saw in my little diagram here. It's one server and one database. So what type of scale are we going to be talking about? Are we talking about the number of requests per second, like I demoed with Insomnia? Are we going to talk about the complexity of the code? That's another type of difficulty that comes with scale. The size of your dev team, or the joke one, how many managers there are in a room. But scale, it can come in many forms. And what I want to concentrate on today is the number of requests that we're dealing with, the load in the transactions per second your website is dealing with. So there is two types of scaling that you can do. There is vertical scaling and horizontal scaling. Vertical scaling is where you take your one machine and you make it a bigger machine. And now it is going to be able to handle more whatever. And if you hit the same scaling problem as the system grows, then you just take that big machine and you make it an even bigger machine. And you can imagine that Google, Amazon, Microsoft, who offer these cloud computing things that we're all running our servers in the cloud, they actually have a limit to the size of the machine. You can only have such a big computer. So there is a limit with vertical scaling. It's also very cost expensive when you get into specialty machines. The other type of scaling is horizontal scaling, where you take your one machine and same size machine, you just say there's two machines or three machines or four machines. That is, usually you can cost optimize, you can optimize your costs there for the cheapest per CPU or per bandwidth or what have you. And those are great, but a little harder to implement at first. Just putting more coins in the machine for a bigger computer is easy. Putting more, figuring out the infrastructure so that you can use those three computers or however many you have is a little harder. So the infrastructure for horizontal scaling takes a little more work, but that's probably what we should lean towards in general. Initially, we may do the vertical scaling for the fast, quick solution, and then down the road, horizontal scaling. So this infrastructure that we have, it could get bound, it could hit its scaling limit or its current infrastructure limit in a couple of different ways. So the constraints of the system. If you have something that is taking in a lot of requests per second, and the network card is what is the limiting factor, that's I/O bound. If it's something like our system here, which is processing a fair bit, this one is CPU bound, other than my bad coding, which loads into RAM a 50 meg file every time. So if we had that stored in RAM, it would be a CPU bound problem because it's doing a lot of image recognition. And then storage bound, like RAM storage or physical hard drive storage could also be another constraint. So the system's growing. We eventually need to, we put our coins in the machine and we use the vertical scaling trick for a little bit. But the boss comes to us and says, we can't keep scaling vertically. It's costing us too much. Figure out a cheaper solution. So this is what we're going to do. We introduce a load balancer. So what a load balancer is it's a concept that is distributed under the hood. It's great that way. And when a request comes to the load balancer, it gets redirected to a server behind the scenes that does the work, writes to the database, thinks about it for a while, and then eventually responds back out. I didn't draw the backwards arrow from the server through the load balancer, but the load balancer can distribute in a couple of different ways, and this is, I find interesting. It might be too in-depth, but you can randomly choose which server it goes to. You could round robin, like you could go A, B, A, B, A, B back and forth, or A, B, C, A, B, C, A, B, C, choosing which server you're sending your request to. Or you could actually look at the server and see how much load it is having on it at this point, because this one's handling a big request. So you go and redirect over to this other server. That is a more intelligent approach, but a lot of people actually still use round robin or true random because it is less CPU intensive for the load balancers. Okay, we've done that. Life is good. Our system is working at a higher load. And then eventually we come back and it is load balance. It is starting to act too slowly for some of the users. So the boss says, make it faster. Put more, make it cheap, but make it faster. So this is what we're going to do. And this is the demo where we're actually going to code this. A request comes in. What is this a picture of? It gets put on this server. This server doesn't do any of the work. It is now going to just write some data to the database. And then it's going to put a little token on the queue. It's going to put a message on this queue saying, do this work down the road. And then it's going to respond right away to the user and say, the picture you gave me, we've stored it, and it's now going to be X, ID X. The user eventually comes back and says, what is this a picture of? And asynchronously, at some other point in time down here, the work has been done and it's going to ask, and the server will know, and the server will respond. It could ask and the server might not know yet. So it'll keep asking until it knows. So that's polling until it works. It's not efficient, but it works. So what the consumer does in this situation is and you can have as many consumers as you want, it's easily distributable in that way, is you take a message off the queue, you do the work, you record stuff to the database, and then you delete the message afterwards. I'm using in this scenario an SQS queue. That is something that Amazon provides. And I want to talk about the specific implementation of this because it provides a very nice contract for the consumer and the queue to interact with. Because consumers can be turned off at any point in time, or they should be allowed to be turned off, on and off at will, the work might be half done when it gets turned off. And now this consumer that took a piece of work off the queue has started to do the work and then gets turned off. You don't want that work lost. You don't want that analysis of the picture to come up with the tags to be, that user will never get the tags. So what you want is that queue has the message reappear on it if it doesn't get deleted within X amount of time. So now you can have another machine turn on because the work was half done, pick it up, and then redo the same work and write it to the database and then delete it. And now you've got that work officially done and it won't reappear. SQS queues are beautiful that way. They're distributed under the hood so they can scale with your system. Matthew may know that his system at his company uses a lot of queues, and they are SQS queues. I used to work there. They're beautiful. They allow the system to scale massively. So let's get into some coding. Ooh, what is this a picture of? Oh, some talking notes. So here's our code. I have talking notes in there. This is all public. If you want to go and pull it off of GitHub, you're welcome to. There is this thing called a proc file. It tells you, first of all, Matthew, is this font big enough? Can people read this?
I mean, just a reminder, you can double click the slides to make it larger.
Oh,
so anyone should be able to see it.
Awesome. Awesome, thank you. Okay, so this here is saying there is a machine that is called web, and this is how you start it. So what we're going to do is we're going to introduce that consumer machine. I'm going to call it consumer. I'm fancy that way. Consumer.py. And then I'll have to write that file. What this does, what this web one does, is it eventually starts this main file. And what happens in here is it serves up the static files for the website. If you push a picture to it, this is where you push a picture to it in this function, and you can only post. If you want to know information about a picture, you can get from here. And if you want a list of all the pictures, you can, and then this is how it starts. You don't need to know any of that, but just a tour of the code. So this is the code that currently is in use. When you upload a picture, we get the image ID off of the image. We get all this temp information for this file, and we break it apart into these three pieces. We come up with the file name that we're going to store it as, because we're going to push it up into some storage system. You don't need to know what S3 is, but that's where I'm putting it. So I'm putting it publicly up here, and I've uploaded it. So you give me a picture, I put it somewhere public on the internet. And then I do all this processing work. This is where we do all that CPU processing, and we look at that picture, and we come up with the tags, and then we write it to the database here. So what I'm going to do is say, let's not do that work right now. It's an empty list. We have no tags. Instead, I am going to put message on SQSQ. I'm going to put the image UID. So that's going to be the message that goes onto the queue, the ID of the picture that we want you to analyze and come up with the tags for. So now we're going to go and create ourselves a new file, consumer.py. Now let's see if I can write some code. While true, forevermore, we are going to get the message, what is it? Let me think about this. It was get message from SQSQ, I think. So let's see. Yes, I wrote it right. I'm auto importing the function that I wrote, so we don't need to worry about the details. I already created the queue, and here's this message that we got off the queue. Now the image ID is in the message body. I believe it's body. So now you get this message. It's got this string that you can read from it. There's a bunch of other information about the message that we don't need to worry about. And then we go and grab our data. Equals get image with the image ID. Did I write that function name right? Yeah. Okay. And now, once we've got that data, we are going to, because it's stored in S3 right now, we need to pull it down onto our own computer or onto this server. So load to a temp file, data, and that data blob has in it something called S3 path. Okay, you have this file locally on your machine. Very simple. Now we do the actual processing work, and we figure out image tags for path equals the path. So then now you've done all that processing work. As the diagram had shown, you pull the message off the queue, you go and do the work, and then you write it to the database. So now we're going to say update image tags. This is what we were doing before inline. For this image image ID, and that comma separated list of tags. And then when we're all done, we delete the message from SQS. This message. There we go. Very simple. Now we have the function that you hit at first on the web server. And we can get rid of that comment. We take in the image, we push it up somewhere, we say, go do this work, and we put it on queue. And then here we take the work, we actually figure out the tags, and then we update our database. And now, when somebody wants to know about it, we can come back over here to get all the info details on that particular picture. This is where I would totally deploy this code, but as I've figured out through practicing this presentation, don't deploy things on the weekend, don't deploy code half-baked. I should write some tests around this. This is production, so let's be safe and go and write some tests down the road. But I won't do that during this slide. So I've given you this bit of logic, but now let's talk about a little bit about Reentry Code and then review that function that we wrote, that infinite loop that's pulling messages off the queue. What happens if the server dies halfway through? What happens if it dies after it's figured out all those tags? How can we avoid redoing that work? That work is if a message disappears off the queue and reappears every once in a while, it's okay to do a lot of work to redo it. It's not that expensive. But if we are turning off our machines, if they turn on and off a lot, then we're doing extra work. We're duplicating work where we don't have to. So we're wasting computation time. That wastes money. A little bit of wasted money. Who cares? A lot of wasted money. Yeah. Boss comes back and says, make it more efficient, please. So, reading through this, can you spot where, if the computer dies, it has already done the work? Keeping in mind that on line 12, we do all this work, and on here we delete it. So anywhere within 13 and 14, if something dies, then we're still redoing all that calculation of that, figuring out the tags. So what we have to do is, if we've written it to the database, so actually only 14, there's something that's different here. So we can come along and say, over here, when you turn on this machine, or when you get the message off the queue, you get the image ID, you get the metadata around it. And in that metadata, we have all the tags. Now, the tags are going to be empty unless we've written, unless we've done the work. So we can just go and check that. So if the tags, if we have more than one tag, then we've already done the work. So you can just say delete the message from the queue. And we can then go back. Now, if you get a message and the work's already been done, you're not going to have that work to do again. You just say, this work's been done, delete the message from the queue and keep going. And now your system's a lot more efficient. Excellent. Let's go on. So this is taking a bit of a detour from our scaling of the code into those distributed ways, and it's talking about the database. If you are if you have multiple web servers and if you have multiple queue, and the load balancer is distributed under the hood, so if any piece dies, it's going to be fine. If multiple web servers, then one of them dies, you're going to be fine. A few requests may disappear, but the system will continue to survive. If you have a queue and it's distributed under the hood, and any piece of the queue dies under the hood, then it's going to then it's fine. It's going to be able to recover. Queues are distributed by nature. If you have consumers and they're distributed, and you say you have lots of them, yay. Any one of them dies, and the work reappears on the queue, and no work gets finished. Or say, all the work continues to get done. If your database dies, then everything stops and explodes, figuratively. So, this database has to be protected in some way. And the way you do it is you can have a second database. This is a backup database that you're running. And we call this a high availability, or HA for short, database. And it's a backup copy that's running in parallel, and a snapshot of the database gets loaded into your backup continuously every couple of milliseconds. So now if the database dies, the primary one, the secondary one becomes a primary, and you only lose a minuscule amount of work, and the system keeps surviving. HA is a beautiful thing. It's a production system, so we're going to throw that into it, because you're going to have to pay twice as much, one for each server, but it's worth it in case the database dies. Then what happens if that one database, or if it's HA, it's still, you think about it as one database, starts to act too slowly just to the amount of reads and writes that are happening. You can actually split it up. You can use that same infrastructure that has the HA aspect to it and make multiple replicas, but then read from them instead of just having it a shadow and not used. So you can write to one machine and read from the replicas, and you can pick whichever replica you want to read from it. You have to know that you've got a little bit of latency in the there's latency in the replicas getting up to date and getting that snapshot pushed to it. But it's actually quite an efficient system, and they're doing batch snapshots. So under the hood, depending on the database type, master replica setups are quite efficient, and you can get a lot more computers reading from the one data store. So you can have your servers, and you can have your consumers, and whatever else may interact, all write to the master and read from the replicas. Excellent. So the system keeps going. We can do it this. We can add this when you have so many servers, consumers, everything talking to the master, that you are starting to have the bottleneck be the interactions with the database. This gets you farther. Another way you can do this is you can actually shard the database, or the data inside the database, and put it on two databases, or three or four. All the odd data goes onto database A, and all the even data goes onto database B. It's a simple way to do it. Now you have to have a little more logic for figuring out where to go and get your data, but it's another way you can scale your data. Okay, we've got to the end of this. It's been a fair bit of different concepts, so let's go over it and scale this one system that we had at the beginning, and slowly add in pieces at a time and add the complexity to this system as the system grows. So we start with a picture. What is this a picture of? Being pushed to a server, synchronously thinking about it, and then writing to a database, writing storage, whatever, and responding with the list of the tags that what it is a picture of. The system grows. We need to go and scale this farther. We need to add more servers to it, and we can either scale it vertically or horizontally, and eventually we're going to have to scale horizontally, so we add a load balancer and multiple servers behind the scenes. Now, you're doing two types of work here, basic web requests, and that's heavy CPU load for the figuring out the tags. Heavy CPU load probably should go on some other server somewhere, and then you can pay for, things with good network, for servers with good networking speeds for these web servers, and you can pay for the ones with good CPU for the consumers. So that's what we go and do. We implement it. We scale it a little farther. We just wrote it. We now have a system that is able to take asynchronous work and do the asynchronous work and respond with what the tagged picture is. But now the logic is being done in this machine, or the processing and figuring out of the pictures. We add in the HA database when we realize that we might have some system vulnerability issues for any sort of outage. So now we have 2 databases there, and we're feeling a little more comfortable about sleeping at night. And then we realize that we're starting to get a bottleneck with all these servers and consumers that keep scaling up. We add more of them because we're getting more load. So we eventually make replicas off of the HA primary database. And these replicas get read from all of these different machines, and these machines only write to the database, the primary. And then we shard it. So now we have HA databases with replicas running. This is a simple little bit of code that we wrote. It took me half a day to write. It is not a simple piece of infrastructure, and this is okay to look scary. This is what you're going to walk into in your job in the industry. If you get a new job somewhere, you're going to have some system like this. But realistically, under the hood, all it was that simple couple hundred lines of code that is used to figure out the picture of figure out what the picture is of. This is what I find interesting in, and why software development is cool to me, and continues to be interesting all the time, is because that scale problem that you encounter and that you have to adapt and adjust for bottlenecks continues to always introduce new interesting bottlenecks and problems, and you always have to have another solution for it. So that is my slides. Thank you very much. Happy to answer any questions at all. I probably should have put something on here saying I'm in YYJ Tech. Feel free to reach out to me at any point in time. I am John Oram in YYJ Tech. So, yeah.
All right.
Thank you.
Thanks, John. Thanks, John. We're now open for questions. We still got about 15 to 20 minutes into the end of this session. So looks like we already have a question there from Ricky. He asks, do web apps running on cloud services like AWS or Azure do the distribution automatically, or is it something we must configure, implement ourselves?
Okay, that's a great question. It depends on what service you use. So I'm sorry, it's almost every question is going to be it depends. But if you're using serverless infrastructure, then it's going to be distributed by nature. If you use an EC2 instance, if you pay for a computer and then set it up yourself, you're going to get you're going to have to deal with all of the redundancy yourself. So the distribution, there is a single button in AWS. I'm not sure about the other. I'm sure they do, where you can just say HA please, and it does it for you, because you're paying twice as much and they want to encourage you to spend money. So it's also a really good feature. So HA, you can very easily just toggle on. Distributed web servers, harder to do, but they provide load balancers for you. Most cloud service providers will provide load balancers that you can use. you have to actually say, I'm going to use that and I'm going to route my traffic to it. And then it's going to go, and you have to configure it. But you don't get it by default. So hopefully that answers your question. But in the old days, it was a lot more manual, and they've given you a lot more tools these days to basically be able to introduce these, to do these best practices that you have lying around of like, yeah, you should have everything redundant. And if you do, they'll try and encourage that. But no, not by default. At least it used to be. Okay, Annie asks, thank you for your presentation. Could you go over what replicas are for again?
Yeah,
sure.
While you do that, I can
I'll just
take
jump
the
back
time to remind everyone that this session is being recorded, and the recordings will be available in the LinkedIn group. I posted the link just a little bit above in the chat there. Go ahead.
So in this slide here, there is 3 different databases you can read from, and 1 you can write to. Here, it's all the network traffic is going to a single machine, and then that's being cloned behind the scenes for the HA. So you get a lot more bandwidth to your database, so you can do more requests per second. The other part of this is that there's some efficiencies involved with that replica from the master to the slave. So there isn't a lot of extra overhead there. I just want to mark that your database designers, people who've created Postgres, MongoDB, Redis, whatever, they're not all databases actually, but they're data stores and yada yada. Let's not nitpick. But Postgres, for example, they have designed this perfect little backup mirroring system that does it very efficiently. They've done it so that this becomes a more efficient system. When you write to the master, there is the reason that it becomes slow partially is because writes can lock tables or objects inside the inside the database, and reads off of it sometimes have to wait for that lock. But if you know you're on a different machine, then they don't do that. So the writes here can just continuously write to the table without interfering with these reads. So reads happen faster. And there is less bandwidth to the master, so there is or less usage of writing to the master because there's no bandwidth to more write. So just reviewing your workload. Hopefully I answered Andy's question there. I went into a bit more depth.
Next we have a question from Lawrence. Questions about what you're using for messaging queue, and if you have a favorite.
Okay, I love SQS. I am biased. There's a bunch of other structure that you can use, and if it is a queue that you need, I like SQS. I like other systems in other. Google has PubSub or whatever it's called, which can be used as a queue, but can be used as more distributed, more complicated system. But because data can be forked and routed appropriately. And you can use multiple queues, but anyway. So I used SQS in this example. Actually, let me show you all of the code for the SQS. Here's put message on a queue. Here's get message from a queue. It's using an SQS queue that is called, what is this picture of tag processing. And it sends a message. It's very simple. And it goes and takes every single message, only one, and it times out. There is a concept in SQS that I love. And again, Matthew, I used to work at your company, so I'm going to tell you a little something. We saved like $5K a month by turning on long polling. I literally putting in, or some large number, like by putting in wait for X amount of time. So you get this message off the queue, but if the queue's empty, wait there until there is a message. Don't keep asking for messages off the queue every time, because you're paying per call to the queue. And queues are stupidly cheap, but we were very distributed in that point in time, and heavily loading this queue, or there are these queues, plural. But if you wait for this message, then you're not making 30, 40, 50, 60 extra blank calls with nothing in them. So that's something I love about SQS. You just need to remember to turn it on.
It's awesome.
Awesome. And Rick says thank you. Or Lawrence says thank you. There you go. Okay. If there's no other questions, thank you everybody for your time. And if you come up with any questions down the road, please do.
Yeah, I just have one quick question for you, John, and also giving the time for anyone else to put any other questions in the chat. But I mean, there's some sort of trade-off between scaling out and up. You mentioned, so scaling up, there's a limit, and it can get quite more expensive. But you still have to pick a size for the server scaling out. So should you go for the smallest possible, or should be like halfway, like a mid-size server? Or is that something that only experience will tell you?
No, you can experiment. You can do this through experimentation. I love that question. That's great. Take a bunch of different types. Like, you're probably going to figure out that you need more RAM or more CPU or more I/O, like what your type of workload is. Now, in this diagram here, I mentioned that this is mostly I/O, and this is mostly CPU. So when you choose your server type, you can sort of pick and make an educated guess in that sense of what your bounds are going to be or what your constraints on your system are going to be. But if you have it distributed horizontally, you can go and run 5 machines on your queue of type X and 5 machines on your queue of type Y, and then go and see which ones perform better. Look at the metrics, and you can do cost per request done. So if I were asked that question by in a production system, again, cough, cough, you've got the perfect system at Send With Us and dispatch those internally. You can go look at this, and the machines that are taking off the queue, go and compare and contrast on different queues, and just time how many requests you're doing per hour, and then look at the cost per hour. Now you can have cost per request calculated. And you can do that for multiple different types of machines. Do it through experimentation and you get a better result. You can actually empirically find that machine X is best for cost per dollar. There's also a knee-jerk sort of like middle ground that is sort of cheapest. And the cloud providers will encourage you to move towards the latest servers so they can turn off the old ones. So there's a min-maxing plan you can do there. And you can even pay for, there's 2 types of machines in. I think this is in every cloud provider, but AWS definitely has.
Right. Pay
for it ahead of time and get discount. There is pay for it off the shelf, turn it off, and you're not paying for it anymore. And there is pay for it as long as you're the highest payer. Otherwise, we're just going to take it and take it to somebody else. Those are super cheap. They're great for this sort of consumer problem, because now you throw 90% of them as these ones that might randomly turn off, but you're paying 10 cents instead of $1 for them. So you don't care. You just throw more of them at it. It's great. But keep a couple of them to be the type of machine that is always on, that you're paying for. At your, and those that can be cheap too. You can pay for a long run of them. Pay for the year ahead, because you know that you're going to be using the types of machines for a year. But use the cheap ones that you can get away with, and you can save a lot of money.
Yeah.
It's a game that min-maxing that I love to play. Yeah.
Yeah.
Hopefully that answered your question. Annie asked, I see, thanks. What's making sure all the replicas are up to date and synced with the master? The master knows about the slave, or the replicas. Here. The master knows about the replicas. It has a list of them, and it pushes the update to each of the replicas. So when you add a new machine, you have to go and update the master, and then it knows about that fourth machine, and it's writing to them each time. So and you can tell it how frequently you want it to do those pushes. I'm talking about Postgres in particular. I don't know about all databases, but with Postgres, you can tell it the periods, how frequently you want it to push to the replicas, because it does take CPU and I/O. You can actually have replicas off replicas. You can do a bunch of really weird stuff. I don't recommend it, because then that daisy chaining of databases gets complicated and flaky. But yeah, it's just the master knows about the replicas, so the master then pushes the data to the replicas. Okay. Also, thank you to COVID. This has been a quiet background to my office space. I have come into the office to give this talk, and that's why I'm looking at multiple screens. But I hope everybody's enjoying lots of blank desks in the background. Okay, I think that we've run through all the questions, so yeah. I'm going to drop off now. Thank you so much, everybody.
All right.